This is linear second order equations, and in this video we will be talking about homogeneous linear equations and the general solution. So let's go ahead and begin with a linear differential equation with constant coefficients. So here are our constant coefficients. So A, B, and C are constants, and we also have a homogeneous equation. And we do have a second order DE. Okay, let's take a look at these, at this differential equation. As you can see, the solution of this must have a property that its second derivative can be expressed as a linear combination of its first derivative and itself. So this suggests us finding a solution of the form y equals e to the RT. And we like this solution since the derivatives of this function, they are just constants times e to the RT. So let's go ahead and use these and substitute them into our given DE. I'll go ahead and rewrite this. And let's substitute those in. So we have A, R squared e to the RT, plus B, R e to the RT, plus C e to the RT is equal to 0. Factoring out e to the RT, you can see that we have AR squared plus BR plus C is equal to 0. Now, since e to the RT can never be equal to 0, it must be that AR squared plus BR plus C is equal to 0. And this is just a quadratic equation with roots R1 and R2. And that leads us to this solution, or these solutions right here. Y1 is e to the R1 times t, and y2 is e raised to the R2 times t. Now, if you can see here, we come up with a general solution. This is our general solution. And basically what it says is that since both of these solutions are linearly independent, this general solution here provides every linear combination of both of those solutions. So let's go ahead and try an example and see what we have here. Find a general solution, and I'll leave that there, to the differential equation y double prime minus y prime minus 2y is equal to 0. And I might add here that this equation here is called our auxiliary equation. Let me change that, it's a little bit dark. It's also known as a characteristic equation. So we can actually go right to that equation when we are solving these. So let's look at this example, find the general solution to this differential equation. So as you can see, our auxiliary equation is going to be r squared minus r minus 2 is equal to 0. And we can factor that. R minus 2 multiplied by r plus 1 is equal to 0. So we have r is equal to 2 and negative 1. So we could say that r sub 1 is equal to 2 and r sub 2 is equal to negative 1. So therefore, our general solution is equal to y of t is equal to c1 e to the 2t plus c2 e to the negative t. And keep in mind that c1 and c2 are just arbitrary constants. Okay, let's look at our next example. Find a general solution to this differential equation, 6y double prime plus y prime minus 2y is equal to 0. So our auxiliary equation is 6r squared plus r minus 2 is equal to 0. And we can go ahead and factor that. I'll go ahead and just do that very quickly over here. We have a negative 12 and a positive 1. So we have a 4 and a negative 3. And dividing these by 6r. And we come up with negative 1 over 2r and 2 over 3r. Okay. So that leads us to three r plus 2 multiplied by 2r minus 1 is equal to 0. So we have r equals negative 2/3 and r equals 1/2. Therefore, the general solution, and we'll just go ahead and put R1 and R2 here. And we can say that our general solution is y of t is equal to c1 e to the negative 2/3 t plus c2 e to the 1/2 t. This can also be written as e to the negative 2t over 3 e to the t over 2. Okay. Let's take a look at our next example. Find a general solution to this differential equation, 3y double plus 11y prime minus 7y equals 0. So our auxiliary equation is 3r squared plus 11r minus 7 is equal to 0. And as you can see, trying to factor by hand, we don't get anywhere. So we can't hand factor. So we will use the quadratic formula. So we know that r is equal to the opposite of 11 plus or minus the square root of 11 squared minus 4, and a times c is a negative 21 all over 2a, which is 6. So we can simplify this as negative 11 plus or minus the square root of 205 all over 6. So now we have our general solution is y of t is equal to c1 e to the negative 11 plus the square root of 205 t all over 6 plus c2, let's go ahead and bring this down here, e to the negative 11 minus the square root of 205t all over 6. Okay. So what happens if we don't have two distinct roots? So here we have two roots plus or minus. Here we have two roots distinct, negative 2/3 and 1/2. But what happens if we have the case where we have what we call repeated root? So we factor our auxiliary equation and we have repeated roots. Then this will be our general solution. As you can see, there is an extra t placed in here. So c1e to the rt and c1e to the rt are not linearly independent. So if they are not linearly independent, then we cannot write a combination of them as our general solution. So we then will use this additional t. And you can convince yourself that if c2e to the rt is a solution, so let's see if I can write that here with a lighter color. If c2e to the, whoops, let me do c1. If c1e to the rt is a solution, then c2te to the rt is also a solution. Okay, so let's see what happens here with this repeated root. So find a general solution to the differential equation 4 double prime plus 20y w prime plus 25w equals 0. So let's see what we have here. So let's write our auxiliary equation. So we have 4r squared plus 20r plus 25 is equal to 0. And factoring that, we have 2r plus 5 multiplied by 2r plus 5 equal to 0. And you can see that here. So we will have 100 and we will have 20. And of course, that's 10 times 10. And dividing by 4r, we can simplify as 5 over 2r. And that's where we get the 2r plus 5. And that would be the same here. That would be equal to 5 over 2r. Okay? So now, what do we have? R is equal to negative 5/2. And what we have here is a double or repeated root. So, therefore, the general solution is going to be y of t equal to e to the negative 5/2 t. Whoops, I forgot my C1. Plus C2 t e to the negative 5/2 t. So we have this t right here. Okay, now let's go on to an IVP. We're going to solve an IVP. So here we have our differential equation, and here we have our initial conditions. So we have our IVP. Okay, so we're going to solve this in the same way. We're going to write our auxiliary equation. So we have r squared plus r is equal to 0. And we come up with r is equal to 0 and r is equal to -1. So our general solution is going to be y of t is equal to c1 e to the 0t plus c2 e to the -t. And of course that simplifies to c1. And you know what? I think I'm going to write this the other way. You can actually write them either way. But I usually like to put my constant last. So let's go ahead and put c1 e to the -t plus c2 e to the 0t. And then we come up with c1 e to the -t plus that second constant. Okay, so now we need to satisfy the initial conditions. And let's go ahead and have y of 0, and that's equal to c1 e to the 0 plus c2. And so that was given to be 2 is equal to c1 plus c2. And we could go ahead and now take a look at our first derivative. So y prime of t is going to be the opposite of c1 e to the -t. So y prime of 0 is given to be 1. So we have -c1 e to the 0. And that's just going to be the opposite of c1. So we can see here that c1 is equal to -1. And so plugging in a -1, we can now see that c2 is equal to 3. So now we can write our solution to our IVP. And I am going to make all of this just a tad bit smaller so that we can put our our particular solution, our solution to the IVP. And we will now have these constants. And so our solution to the IVP is y of t is equal to -e to the -t plus 3. Okay, let's take a look at our next example. This is also an IVP, and we're given z double prime minus 2z prime minus 2z is equal to 0, and we're given two initial conditions. Let's go ahead and write our auxiliary equation. R squared minus 2r minus 2 is equal to 0. And so we have r equals 2 plus or minus the square root of 4 minus 2 times 1, which is 2. Whoops. So that's b squared minus, and that would be multiplied by AC, which is a -2, all over 2. And so here we have r is equal to 2 plus or minus the square root. Well, I think I'm going to try that one more time. 4 minus 4 times 1 times -2. So we have 4 plus 8, which is 12, all over 2. And of course we have 1 plus or minus the square root of 3, since that 12 is 4 root 3. Okay, so with that, what we can do is we can write our general solution, and we have y of t, and this would be z of t. So z of t is equal to c1e to the 1 plus root 3t plus c2 e to raised to the 1 minus root 3t. Okay, so now let's go ahead and find z prime. And here we have z prime of t as c1 multiplied by 1 plus root 3 e to the 1 plus root 3 to the t power plus c2 multiplied by 1 minus root 3 e to the 1 minus root 3 times t. So let's go ahead and have check our initial conditions. So we have z of 0 is equal to 0. And there we would have just c1 plus c2. And that's equal to 0. And so you could say that C1 is equal to the opposite of C2. That will be handy. And then let's go ahead and look at Z prime of 0, which we're saying is equal to 3. And that is C1 multiplied by 1 plus root 3 plus C2 multiplied by 1 minus root 3. And that's going to be equal to 3. We already know that C1 is equal to the opposite of C2. And we'll just do a little algebra. And doing a little algebra here, we can see that 3 is equal to, and you will have negative 2c2 root 3, and I'll go ahead and solve that for you. C2 ends up to be the opposite of the square root of 3 over 2. And that means C1 is the square root of 3 over 2, since it's the opposite of C2. So now we can go ahead and write our particular solution or our solution to the IVP. And so let's go ahead and do that. We have z of t is equal to the square root of 3 over 2 e to the 1 plus root 3 times t minus the square root of 3 over 2 e to the 1 minus root 3 times t. We could go ahead and factor that square root of 3 over 2 out, and you can see that we have e to the 1 plus root 3t minus e to the 1 minus root 3t. Okay. Let's take a look at our next example. Solve the IVP y double prime minus 4y prime plus 4y equals 0, and we are given two initial conditions. Let's write our auxiliary equation. We have r squared minus 4r plus 4 is equal to 0, and we come up with r minus 2 all squared, or we can write it as two binomials multiplied together. So we have a double root, r equal to 2. So this means that our general solution is given as y of t equals c1e to the 2t plus c2t e to the 2t. So now let's go ahead and use our initial conditions, but I like to go ahead and find y prime at this point, but you can do it at any point. So we have y prime of t is equal to 2c1 e to the 2t plus 2c2 t t e to the t plus c2 e to the 2t. And now we can go ahead and use our initial conditions. So we have, I can just do it right to the right of that. We have y of 1 is equal to c1 e squared plus c2t e squared. And that is going to be equal to 1. I will go ahead and write that up a little higher. And that's 1 is equal to c1 plus c2 all times e squared. Okay, and then let's go ahead and see what we can put these together later, but I'm going to go ahead and find y prime of 1, and that's going to be equal to 1, and that's 2c1 e squared plus 2c2 e plus c2 e squared. And I can see right here that should have a 2t, which means this is going to have a square. And now we can gather our e squares as 2c1 plus 3c2. Putting these together, we find that c1 is equal to 2e to the negative 2, and c2 is equal to the opposite of e to the negative 2. Therefore, the solution, and those are definitely linearly independent, placed back in front of our solution here because of that t. And we come up with y of t is equal to 2e to the negative 2, e to the 2t, minus e to the negative 2 times t multiplied by e squared, e to the 2t. We can go ahead and try to factor out an e to the 2t, and we can see that that's 2e to the negative 2 minus e to the negative 2t, which brings us, and I can actually move this up a little bit, to a nice simplification. We can now also factor out an e to the 2t, but we can factor out an e to the negative 2. So we can place that in the exponent, and we're left with 2 minus t. So any of those solutions, but this is very nicely simplified. And that concludes this video.